Bueno, muy buenas tardes. Comenzamos la ronda vespertina de los cursos. The next lecture is the second lecture of the Professor Carmen Nuñez. That is the introduction to the superstring. And after that, we have the coffee break. And after that, we have the discussion section. Then there is no time for questions right now in the discussion session. We can ask any question.
Okay, so let me summarize a little bit what I did yesterday. We constructed the action for the periodic string, which turned out to be the coupling of supersymmetric, n equals 1 supersymmetric matter fields, let's say the x mu and the psi mu, to supergravity in 2 dimensions. So, this we construct. This is basically supergravity in 2 dimensions, coupled to this supersymmetric matter multiplet, and we saw that that action had several symmetries. So I will list here the symmetries of the action: supersymmetry, Weyl symmetry, local superwide. These are the symmetries on the worksheet. Local Lorentz. Lorentz symmetry. What else? Reparametrizations. And we were able to use all these symmetries in order to gauge away some components of the line in 2 dimensions, and to gauge completely away the Repitino. So using these symmetries, we were able to fix the gauge and write the line precisely as the delta function, and the Gravitino was completely gauged away. And after doing that, we were left with an action which is basically this one. So here I was using like coordinates on the worksheet. So we define these coordinates, sigma plus and minus, minus sigma, and derivative plus minus means derivative with respect to sigma plus and sigma minus. Sigma. So we arrived at this action, which is a gauge fixed action, and so these symmetries allowed us to fix this gauge, which is called the superconformal gauge. And then we derived the equations of motion. The equations of motion for the x fields were basically the wave equation plus and minus x mu, and the equation of motion for psi, this one. And we also mentioned that even though we fix the gauge, we cannot forget about the equations of motion for these fields, which will then turn out to be constraints on the solution of the theory. So the solutions of the theory will have to satisfy the constraints arising from these equations of motion, which these equations of motion are basically the equation of motion for the vine, which is the energy momentum tensor, and for the gravitino, which is the supercurrent. This F here refers to the fact that it is a fermionic field, and it has only one index of the worldsheet. Okay. So, okay. So, are there questions? This is clear. So we basically solved these equations. So we didn't write the explicit solution, but we saw that this equation here implies that the x mu can be x mu of sigma can be split into a left mover function of tau sigma plus a right mover function of tau sigma, exactly as in the bosonic string. And for the fermions, this if LASS psi minus equals 0 implies psi minus is a function of psi minus, sigma minus. Psi minus is a function of sigma minus, and similarly psi plus is a function of sigma plus. Okay? So, okay, so basically these were the solutions to the equations of motion, but then we have to impose the boundary conditions. So when we vary this action with respect to the fields, to x mu and psi mu, there are boundary terms which have to vanish, and according, there are several ways to impose the vanishing of the boundary conditions. One is the periodicity of the fields, and this gives rise to the closed string when fields are periodic, or Neumann boundary conditions. For this I mean for the x mu, the x mu. So we have this condition, x mu of tau sigma equals 0 equals 0, and sigma of tau sigma equals L, where L, so this is a string of length L, so sigma takes value from 0 to L. So these are Neumann boundary conditions for the x, and for this gives rise to the open string. And periodicity gives rise to the closed string. So this is exactly as in the bosonic string. There's nothing new. So the new feature here is the boundary conditions for the fermions. So if you remember at the end of the lecture, I discussed the boundary conditions on the fermions, and this gave rise to two possibilities. The fermions, for instance, the fermions can be periodic or anti-periodic because they are fermions, so they can also be anti-periodic. And this gives rise to two possibilities. When the fermions are periodic, these determine what are called the Ramond sector. This is called the Ramond sector of the theory. And anti-periodicity gives rise to the Neveu-Schwarz sector. I write. Someone told me I was going too fast yesterday, so please stop me if you want clarifications. Maybe because of the transparencies, I go a bit fast. But I will try to write so you have time to think. Okay, so for the fermions, we find for the closed string, we had these conditions. are periodic boundary conditions. This gives rise to the Ramon sector, the theory, and the Neger-Schwarz sector. Okay, so this is for the closed string, and for the open string. We were taking the same condition on one endpoint and plus or minus. So for the open string, we have the possibility. So for the open string, that we can have the same boundary conditions on both endpoints or different. So one periodic and another one periodic condition on one endpoint and anti-periodic on the other. So they are independent. So the important thing is the relative phase between the two endpoints. And then again, the periodic conditions, so psi plus at L equals plus, psi minus is the Ramon sector, and the minus condition is the Schwarz sector. Okay, so I think basically we got to this point. Another important point is that we have to take, once we define the boundary conditions, we have to take the same boundary conditions on all directions. All psi mu have to have the same boundary conditions so as not to break space-time Poincare invariance. And we can take, for the closed string, we can take independently boundary conditions for the right movers and the left movers. And then this gives rise to 4 possible sectors. Here, for the closed string, we can have Ramon for the left and right movers. We can have Schwarz, or we can have Ramon Schwarz, Ramon. So these are 4 possible sectors for the bosonic string, for the closed string. And so we will see today that these 2 conditions give rise to space-time bosons, and this here give rise to space-time fermions. And in the open string, the Ramon sector gives rise to space-time fermions, and the Neger-Schwarz sector gives rise to space-time bosons. So this is what I plan to tell you today. What else? We also derived the energy momentum tensor. We saw because the energy momentum tensor and the supercurrent are conserved, then this also implied that we had, say, only the T++ and T minus components of the energy momentum tensor, and this has this form in this case, T plus or minus, I don't know, psi plus. And same thing for minus. And the supercurrent, plus or minus, is basically, except for factors which we not write in here, so plus or minus, T plus or minus X. So basically, this is what we did yesterday. The questions.
Sorry, why don't you write that goes part in S?
Why don't I write?
That goes part injection.
Sorry, I don't understand.
That goes part. That goes action for ghosts.
Ah, ghost.
Yes.
Okay, okay. This so far this is all classical. Okay, this is a classical action. It is true we fix the gauge. So if we want to quantize, we want to do a path integral quantization. We will, in order to do the usual the pop-up determinant, we need to compute it. We need to introduce ghosts. When I do the quantization, I will discuss it. Professor Srivak mentioned this morning, if you want to quantize the bosonic string in the path integral formalism, you need to introduce this system of DC ghosts, which are anti-commuting ghosts, because these are the partners of the commuting fields. Here, we will have to introduce a different set of ghosts, which are commuting, which are the ghosts for themselves. Yeah. If I have time. Okay, so...
Can I ask a question?
Yes.
So, the second line, the Navier-Schwarz condition, so can this be valid for the closed string?
This here, this is for the closed string, and this is
Right.
for the open string.
So in the case of the closed string, in the Navier-Schwarz case,
Yes?
that means that the fermion function is discontinuous when you go around the string?
Yeah, it is antisymmetric. Yeah, you need to give you need to circle it 2 times to get the same sign. This is something which is possible with fermions.
So then, I was just thinking that how will you define the derivative at that point? The function is not continuous if you go around once.
No, but I think there is no problem. But let me think about it. Okay, so let us work out the solution to these equations. I will not do in detail the bosonic sector because it is the same that was done for the bosonic string. So similarly, it is the x mu can be split into right movers and left movers, and then we can expand. We can do an oscillator expansion in this way. So we have the center of mass position of the string, the momentum, the center of mass momentum here, and then we have an infinite number of oscillators. In this way, this is exactly the same as in the bosonic string. We have the alpha oscillators and the alpha tilde oscillators for x right and x left. So this is. Okay. So, and then if we define the zero mode of the oscillators in this way, we say alpha mu naught equals alpha tilde mu naught, and these are proportional to so, or the other way around. We define the center of mass momentum as the zero mode of the oscillators. Then we can write the derivative, plus and minus, as an infinite sum from minus infinity to infinity, where we have included the zero modes here, and in the derivatives, the center of mass position does not appear. Okay, so this is exactly as in the bosonic string. We can also compute the Poisson brackets between the fields, say x mu at equal time, x mu sigma prime. This will be proportional to delta sigma minus sigma prime, and x mu with x mu dot will be 0. And okay, so I won't do that, but it is exactly as in the bosonic string. Then we can replace in the X mu the expansion in terms of the oscillators, and we get these Poisson brackets among the oscillators. So we have alpha mu with alpha nu, and alpha tilde with alpha tilde is like a harmonic oscillator, basically here. Alpha tilde and alpha commute, and then the center of mass coordinates have the standard commutator. So this is the same as in the bosonic string. That was for the closed string, and for the open string, the boundary conditions relate the right and left movers. So I can read it here, but so for the open string, it is written here. So for the open string, we need to impose this condition: derivative of the field at 0 vanishes, and also derivative at the other endpoint. So this gives a combination. There is only one set of oscillators, which I will call alpha mu, and the left and right movers combine the exponentials to give a cosine. So for the open string, we have basically the same expansion, but only one set of oscillators. And from here, the combination implies a different normalization for the momentum. The center of mass momentum and the alpha naught have a different factor, basically, from the closed string. But we can do the same combination here for derivative plus minus of x mu in terms of only one set of oscillators. And again, the Poisson brackets give these standard commutators among the oscillators. Now, if we want to do the same thing for the fermionic fields, then we have to be careful, because we have two different sets of boundary conditions. So the general solution of the two-dimensional Dirac equation with periodic and anti-periodic boundary conditions can be written in this way. So I will run. I will call the indices of the fermionic oscillators with R instead of M. M was used for the fermions, for the bosons. I will use R for the fermions. And then these oscillator modes so now the modes can be integer or half integer. So I will introduce this phase here 5, which takes values 0 or 1, 0 in the Ramon sector for periodic fields, and 1 in the Meshwar sector for anti-periodic fields. Okay, so the sum is over the integers or half integers according to the sector. Okay, and similarly here.
Eso me responde la pregunta de un medio no toma una rada, no toma una, porque le está poniendo un medio. Bueno, es como haber puesto un medio, ¿no? Una raíz. Porque no fue como derivas en el.
A la vuelta. Sí.
A la vuelta. Es como haber puesto. Bueno, le corté el.
Como un branch
Claro,
cut.
como un branch cut.
Sí, como un branch cut.
Entonces tiene un branch cut.
El desarrollo en modos tiene un branch cut, sí.
Sí, es una respuesta.
Sí, sí. Sí, lo que uno tiene que tener cuidado, por ejemplo, cuando calcula amplitudes de scattering, que no aparezcan los branch cuts en las funciones de 2 puntos, por ejemplo. digamos, por ahora en la teoría clásica no nos preocupamos, pero de cuando hagamos amplitudes de scattering vamos a ver que para que la teoría sea consistente, las amplitudes de scattering van a tener que estar definidas cuando no hay branch cuts. O sea, eso va a dar lugar a una teoría unitaria.
Perdón, ¿por qué hay branch cut?
No, acá, ¿no? Porque el desarrollo,
Sí.
el desarrollo es en el sector de Neve-Schwarz. Hay,
Debe ser un medio ahí.
o sea, el branch cuts se entiende si, por eso por ahí estamos,
Es medio diferente.
nos estamos adelantando.
En el Schwarz es un medio. Pero con los lobos.
Por eso.
Sí, por eso.
Ok. Sí, perdón, no sé si eso confundía. No, los branch cuts por ahí se ven mejor si uno hace la teoría en el plano complejo, como hizo Barton esta mañana. Si uno lo ve en el plano complejo, aparecen potencias de Z no enteras. Entonces hay que tratar de evitarlo. Okay, sorry. And one also has to impose for reality, so these fields are real, so there's a reality condition. And similarly for BT2. So the negative modes will be identified with the complex conjugate so that the fields are real. Okay, so this is for the closed string, and then for the open string, again we had a different condition. For the open string, it related the psi plus to the psi minus, so similarly as in the bosonic sector, we will have only one set of oscillators because the boundary condition connect psi plus with psi minus. So this is for the closed superstring, and for the open, we have only one set of oscillators, psi plus minus. Over the integers or half integers. Over the, so if I normalize, if the string takes values, if the coordinate along the string sigma takes values along 0 and L, then I need this factor here, which I have here. So in some textbooks you will see sigma takes values between 0 and 2 pi in the closed string and between 0 and pi in the open string. I prefer to leave it unspecified. It just takes values from 0 to L. Okay. So we have these two expansions. And again, we can work out the Poisson brackets, which now will be anti-commuting fields. Here, psi plus, the equivalent of the Poisson anti-commutators between psi plus, and psi minus will be proportional to 2 pi I delta sigma minus sigma prime. And then these Poisson anti-commutators will translate into these anti-commutators for the oscillators. Minkowski metric, and similar for the tilde. And of course here and the tilde. Anticonductor. Okay, so this is basic field theory, and so now we can, this decomposition we did on the fields, on the x mu and psi mu, we can apply it to the energy momentum tensor and the supercurrent, and then we will find here. But remember, we had for the energy momentum tensor the conservation equations. Equals 0. So as I said yesterday, that this equation implies that there is an infinite number of conserved charges, because this equation implies that T++ depends only on sigma plus. So I can multiply T++ by any function of sigma plus, and it will be also conserved. So we can basically write the charges associated with these currents. I have written in there one prime. So the charge is as usual the integral over the space coordinates. Here it is sigma. Okay, and the same thing I can do for T minus minus. Okay, but then the charges associated with the conserved currents here have this form, and then in particular I can choose a complete set satisfying periodicity conditions for the closed string. Then I can write for this. So I can write for this function a complete set, for instance, exponential. For all integers. Okay, so in this way, so I replace this function here, and I find the so-called Virasoro generators. These are the modes of the energy momentum tensor. They are infinite in number. This n can take values from minus infinity to infinity. And, okay, they're written there. And we can do the same thing for the supercurrent. And I will call the oscillators for the supercurrent, I will call them GR. So we have the Virasoro modes. And similarly for tilde, similarly for L tilde, but we also have the corresponding oscillators for the supercurrent. These are the oscillators for the supercurrent. And similarly for G tilde.
some plus?
Because I am computing them at tau equals 0, so sigma plus and minus is just sigma, because since they are conserved, it's... Yeah. Okay. Okay, so, sorry. Okay, so now, so this is for the, we can define the energy momentum tensor. Unfortunately, I erased it, but the energy momentum tensor now has the contributions of the bosons and the fermions. So, so the Virasoro generators will have a contribution from the alpha oscillators and a contribution from the B oscillators, from the bosons and the fermions. Okay, so from the X mu, the contribution is exactly the same as in the bosonic string. M, and for fermions, So the Virasoro generators will be a sum of the contributions from the alpha oscillators from the X mu and the B oscillators from the psi mu. So for the alpha oscillators, it's exactly as in the bosonic string, and for the fermions, it is basically this product of fermionic oscillators. And the modes of the supercurrent will be a product of bosonic and fermionic oscillators. In this way, so they are fermionic in nature. Okay. So one thing one can see from here is that for the Ramon sector, the indices of the current, of the supercurrent, will be integer, and for the Navier sector will be half integers. Okay. And of course, this is for the open string, and for the closed string, we have another set with L tilde, G tilde, etc. Okay. So again, so if we impose the reality conditions, these generators and then if we use, we want to compute the superconformal algebra, which is the commutators of the Ln with Lm and Ls and Gs all together. We can compute them using the commutators and anti-commutators of the oscillators. Okay, so there are several ways to compute this algebra, but we can use the decomposition of the fields in terms of the oscillators, use these anti-commutators and the commutators for the alpha mu, and then we get the superconformal algebra, which has this form. And this is all classical. I haven't quantized yet. This is all classical. We will see that at the quantum level, they acquire, there is an anomaly. But then this is the usual bosonic Virasoro algebra. Classically, at the quantum level, there is an anomaly, a central charge, which we will work out later. But now we have to compute also the commutator of the LM with the GR. And the anti-commutator GR is fermionic, so they are decompute. And this is accelerated superconductor. Pancho, classical. So n equals 1 superconductor. So there are several ways to derive it. Well, one can derive it from the Poisson bracket. One can essentially it boils down to computing commutators between the oscillators. One can use it for the T++, T minus minus, etc. Or simply replacing the oscillators in the definition of these generators.
Mañana en inglés. ¿Por qué no hay carga central en Virasoro?
La carga central es una anomalía del álgebra. Aparece, ahora lo vamos a ver cuando cuanticemos la teoría, y aparece por los problemas que hay o sea, a nivel cuántico, por el orden normal. O sea, a nivel cuántico hay que definir una manera de ordenar los operadores, bueno, y aparece una anomalía. Pero clásicamente es así. Okay, so my second class was supposed to start now. So is this okay?
Yo tengo una pregunta. Es que no entiendo, lo que no entiendo con respecto de estos corchetes de Poisson. Estos B y los alfa son coeficientes, ¿no es verdad? Son constantes, digamos.
Son osciladores, es como los coeficientes del oscilador armónico.
Ajá, pero digámoslo, son como constantes, ¿no? O sea, no entiendo cómo le puedo tomar el cochete de Poisson, lo entendemos de la forma estándar, ¿no? Como derivada con respecto a las coordenadas, derivada con respecto a los momentos.
Calculamos, por ejemplo, los corchetes de Poisson entre x mu,
¿Sí?
eso lo entiendes.
Sí, claro.
Y ahora reemplazo ahí el desarrollo en modos de x mu y x mu.
Y sale eso.
Y entonces esto me sale esto.
Okay.
Para los coeficientes.
Pero no es que yo derive los B.
Sí, puedes invertir la relación de X a los alfas. Invertir la relación
O sea que
de
lo-
alfa en términos de X y ahí derivar.
Sí, o se puede interpretar como computadores, como claro. Los curvos son anticomputadores porque estos son variables fermiónicas y anticonmutan.
No, pero digamos a nivel de, como dice, ¿no? A nivel del concepto de Poisson. Igual de cambio.
Sí, claro, los fermiónicos. Okay, so the plan now is to quantize. So we have so far done only the classical fermionic string. So now I will discuss the canonical quantization as usual. Then I will try to obtain the spectrum of the fermionic string using the light cone quantization, which is it's not very nice, but it has the nice property that it gives us the spectrum directly in terms of physical fields. Whereas if we do a covariant quantization, then we have to impose the constraints. Okay, I will discuss this, and then I will discuss the spectrum and the GSO projection. Okay, so let me comment a little bit on what we are going to do. So the quantization of the fermionic string is basically, it follows the same steps as in the bosonic string, but now we will find that the critical dimension is 10 instead of 26. So in the bosonic string, we have to impose the Virasoro constraints on the solutions or on the quantum, on the states. And this was the property that allowed us to eliminate the ghost. So in the theory, you have seen in the bosonic string, there are negative norm states, which imply that the theory is non-unitary, so you don't want negative norm states. But we will see that the super Virasoro constraints, in this case, allow to eliminate all negative norm states. And so the new feature here is the existence of two sectors, bosons and fermions, and we will have to study them separately. We will see when we construct the spectrum that there is a tachyon, similarly as in the bosonic string, but we said we don't like tachyons. So we will see that if we impose a projection, which is called the GSO projection, this not only allows us to eliminate the tachyon, but it also gives us a supersymmetric spectrum in space-time. So I will do this here rather heuristically, just to show you. I will try to motivate the GSO projection by saying that we want to construct a supersymmetric spectrum in space-time. So this is, you might say, why? Because, okay, so this is the way to justify that one has to do this. I will discuss tomorrow, because tomorrow we will see if we have time and I am able to construct the partition function. I will show you that there is a consistency condition in the theory, which is modular invariance. And actually, modular invariance implies the GSO projection. So if we want to have a consistent theory, we really have to do this projection, which I will discuss rather heuristically today. So we will see when we do this GSO projection, it will give us two theories, which are called type 2A and type 2B. There are two possibilities to do this projection. And these theories that we will obtain, they are called type 2 because they have two supersymmetries in space-time. So remember, we started with one supersymmetry on the worldsheet, but we will obtain a theory with two supersymmetries in space-time. And these letters here, A and B, refer to the fact that one of them, type 2B, is chiral. So the fermions on both sides, left and right, have the same chirality, whereas here is anti-chiral. So the fermions have opposite chirality. Okay, so this is just for a summary. So we will do a canonical quantization. So now the fields x mu and psi mu will be promoted to quantum mechanical operators, as one does usually in quantum theory. So we will see this is basically what one does in quantum field theory. One promotes the Poisson brackets to commutators, and here the Poisson brackets anti-commuting to anti-commutators, and it is a convenient factor of I there. So we will do the same thing. So these are so the classical equal time Poisson brackets are now converted into commutators, and the anti-commutators for the fermions will be the anti-commutators. Shall I write them again? Necessary. Okay, so we have now the commutators. So we have to erase the I, and you see here that we can basically rescale this AM by 1 over square root of M, and in that case we get precisely the harmonic oscillator commutation relations, and the x mu and the standard canonical commutation relations. And now we have these relations for the fermions. Okay, so for the fermionic oscillators, now I will erase the I, and we have these anti-commutators for the fermionic oscillators. Again, the reality conditions, the alpha dagger will be alpha minus n, and similarly for the fermions. Okay. this is all as usual. And so we will define the oscillators with positive mode numbers as annihilation operators, and those with negative mode numbers will be creation operators, as usual. So if you recall the bosonic string, we had we defined the ground state. Have you seen this in Nathan and in Barton's? Okay, so I'll just review it quickly. So we have a ground state which is annihilated by all annihilation operators, by all oscillators with positive modes. So for M positive, this alpha M annihilate the ground state. So the ground state is determined, it depends, it's not a vacuum, it has a momentum, so it's just the ground state of the theory, defined to be annihilated by all annihilation operators. And again, the momentum operator, it was, remember that it was identified with the alpha naught oscillators. So basically, this P hat refers to alpha naught, and applied on the ground state, it just gives us the eigenvalue is the momentum of the state. Okay? So this is just like in the bosonic string. So now we want to distinguish between Ramon and the Schwarz sector. And this will be the defining property of the fermionic string. Okay? So let me, so this I'm going to go slowly. So the Neveu-Schwarz sector is easy. The Neveu-Schwarz sector is very similar to the bosonic string. We have a vacuum state or a ground state, which is annihilated by all the annihilation operators, Br, because there is no zero modes. Remember that in the Neveu-Schwarz sector, I will do the open string first, and then we'll discuss the closed string. So I remember in the Neveu-Schwarz sector, the oscillators have half-integer modes. Okay, so we can easily see which of them are creation and which of them are annihilation. So the ground state in the Neveu-Schwarz sector will be annihilated by all positive mode operators. Here N positive, R is positive, but it takes half integer values by explicit values. Okay? So in principle there is no problem in the Neveu-Schwarz sector. Now this is Neveu-Schwarz. In the Ramon sector, again, we define the ground state. I will call the ground state A instead of 0. Let's see why. And I will use M because since the modes are integer for both bosonic and fermionic oscillators, I will use the same letter in the Ramon sector. So here M is positive. Or let me explicitly say 1, etc. So I have called this the Ramon ground state. I called it A instead of 0. Because the zero modes of the oscillators, B0, mu. So a state A R, and a state which is B naught mu acting on AR, these two states are degenerate in mass. One can compute the commutator and the mass operator. I will do this in a little while, but one can see that this P naught operator commutes with the mass operator. So states AR and states which are which has a number here. I can take a product of B0 operators for different values of mu, and these two states are degenerate in mass. Okay, so so one thing is important to see if you look at this anticommutator between BR and BS, what one can see is that for the zero mode, B0, this gives the Clifford algebra. Okay. So this is basically the Clifford algebra. So we can identify the zero modes of the Ramon sector oscillators as gamma matrices, gamma matrices. I will come back to this point, but let me first show you that the mass operator. Recall how do we get the mass operator? Like in the bosonic string, the mass operator was coming from L0, from the zero mode of the Virasoro generator. Because, again, because we identified alpha naught and alpha naught tilde with the center of mass momentum. So, so this oscillator, L0,
Creo que los B no eran variables de gamma.
sí.
B al cuadrado tiene que ser cero. Si pongo mu igual a mu, ahí la regla de gamma al cuadrado no va a ser cero. Son de Grassmann, pero tienen esta álgebra, ¿no? O sea que no entiendo qué estás diciendo. Pero no, me varía por un parámetro de Grassmann. Si A es un parámetro de Grassmann, A al cuadrado tiene que ser cero.
Son variables anticonmutantes, ¿no? Pero, o sea, las B no son como matrices de Dirac. O sea, esto lo puedes identificar que son, si querés, también las matrices de Dirac tienen índices espectrales, ¿no? Pero cumplen esta álgebra. O sea, acá también, ¿no? Acá no te molesta porque tienen R y S distintos.
Sí, justo estaba mirando esa ahora. Lo que pasa es que si escribo explícitamente lo que es el corchete ese es, y pongo, elijo, no sé, un índice. Es B0, 1, qué sé yo, al cuadrado,
Sí.
2 veces. Como
Sí.
el diagrama, yo diría que 0, pero bueno, está bien.
Sí, hablamos.
Una pregunta. ¿Por qué los vacíos son diferentes? O sea, ¿por qué arriba el vacío es, lo denominamos como el estado cero en el sector Neuville-Schwarz?
Bueno, en principio tenemos dos sectores y los osciladores fermiónicos toman valores semienteros, en este caso, y enteros en este. Entonces, la diferencia justamente está en estos B sub 0. Bueno, o sea, hay varias diferencias. Ahora vamos a ver, lo voy a discutir ahora, pero vamos a ver que los ground states de Ramón son fermiones, son espinores en espacio-tiempo. O sea, estos son espinores, y en cambio estos, el estado fundamental de Neuville-Schwarz es un estado de spin cero, es un escalar. Entonces, bueno, tienen una naturaleza distinta.
Una pregunta, ¿puede ser que no sea cero porque son operadores y no son números Grassmann?
Son operadores, claro.
Yo con ese argumento no debería venir eso del corchete de Poisson. El corchete de Poisson sí eran variables de Grassmann, no era natural.
Pero es que el corchete de Poisson no es un conmutador.
un archivo inmutable.
No, también, pero uno promueve eso el coeficiente de Poisson a
O sea,
por, así que
en el límite clásico el archivo inmutable es 0, pero el coeficiente de Poisson no.
Claro. Es distinto el coche de Poisson.
Pero a nivel clásico también cambia. El coeficiente de Poisson de feministas.
Anticonmuta. Anticonmuta.
Por eso.
Sí, anticonmuta, pero no se anula.
Pero su coeficiente de Poisson no es el archivo inmutable.
No se anula.
Claro, el coeficiente de Poisson.
Okay, so in the quantum theory, we for the operators we need to define an ordering. So the operator is not well defined unless we define an order. So we define normal ordering. So all creation operators to the left and subtraction operators to the right. And so we can write L0 basically in this way, and there will be again there is an ambiguity in the normal ordering here, especially for L0. And so okay, we will discuss this later. But basically, this is what gives us the mass operator. No, the alpha naught is proportional to the momentum. So and we have the square of the momentum equals minus the mass square. Okay, and here, so for the closed string, one also has the same thing for the L naught. I will not write it. So in the closed string, one has a left mass and a right mass, which are actually equal. These are equal due to the level matching constraint. We call that in the closed string we have this constraint, which basically means that there is no preferred point in the string. So for the closed string we need to impose this, but for the open string we only have one set of oscillators, and so. Okay, so for the closed string. So maybe A is not a good letter. Let me call it. Okay. Mu is the normal ordering constant, and similarly for the right mass. That's mu tilde, and due to this condition, and we'll assume mu and mu tilde are the same. This n here is the level number. It counts the number of oscillators at each level. Okay, so and from here we obtain the mass. Now in the okay, so this here. In the superstring, we also have here actually this is for the alpha oscillator, but we have a similar contribution from the fermions, which has this one, and the sum again is over the integers or half integers, depending by is 0 or 1/2. Here I also define normal ordering. And again, Okay, so there is this ambiguity because of the normal ordering, which gives this infinite sum. So when we anti-commute, if we recall, the commutator between alpha m and alpha n was proportional to m. So when we commute, we get this infinite sum. And okay, so here is basically what I have written there. So the mass square operator is this level number plus a constant, and this constant will depend on the sector. We will have one constant on the Levi-Schwarz sector and another one on the Ramon sector, because we have the sum over the oscillators for the bosons is exactly the same as in the bosonic string, but then for the fermionic sector, we will have a sum over the integers for the Ramon sector and a sum over the half integers for the Levi-Schwarz sector. Okay. So in principle, we have two different normal ordering constants, and the level operator now has this form for the bosonic sector, and this form for the fermionic sector. It has this here, R times B minus R. Because this term here, okay, this is also an exercise. This term here with n, this n is a number, no? And this product here vanishes for precisely because this term, a term of this form, B minus R, B n minus R, sum over n. This corresponds to derivative minus, psi minus, which is 0 because they are anti-commutative. Okay, so this is here. I wrote this here just to write a more symmetric expression, but actually this term is 0. So this is why I wrote there for the level number for the fermions as that form. Okay, so you can see from here that an excitation. So we construct the states. Let us look at the Levi-Schwarz sector, which is easier. So we start from a ground state, and we construct excited states acting with the alpha, with the creation operators on the ground state. So each creation operator increases the mass square operator by m units, and an excitation by B minus R with R positive increases m squared by R units. Okay. Okay. So as I said, in the Levi-Schwarz sector, it's easy. We have there is a unique ground state, which is here. So we can see that when we construct the Lorentz generators, the same thing as we did in the bosonic string. We can construct the Lorentz generators, and we act on this ground state, and we see it has a spin 0 state. Okay, so it is a spin 0 state, and since all the oscillators, the creation oscillators acting on the ground state are have a vector index in space-time. So all the states created on the Levi-Schwarz ground state will be bosons. Okay, so we start with a ground state which is a spin 0 state, and we act on this state with vectors, with operators which are vectors. So they do not change the integer property of the spin. So in the Levi-Schwarz sector, all the states will be bosons. Okay. Now in the Ramon sector, as I said, the ground state is degenerate. Okay, so this is also an exercise for you, but it's easy to see that in the Ramon sector, the V0 operator commutes with m squared. So maybe we can do. So this is the operator which enters in the mass square. So for V0, this the V0 commutes with this for all R. So you see for when R equals 0, this vanishes. So the not commutes with this operator, and so it commutes with the mass operator. So so it means that this state A and this state, which is active on A by the V naught operators, have the same mass. Okay? So the Ramon ground state is degenerate. And as I said, since these operators form a representation of the Clifford algebra, then we can represent these states. So for instance, the state which is active upon by one V naught operator, I can identify the V naught operator with 1 over square root of the gamma matrix. Okay, so I can identify V naught with gamma mu, actually 1 over square root gamma mu. And this, so notice this is a Dirac gamma function, the Dirac gamma matrix in space-time, no? So it is in d dimensions. So mu, gamma mu is d-dimensional. Dirac matrix.
¿Podría repetir de pronto de nuevo el argumento de por qué los estados de network shorts siempre son bosones o se crean?
Okay. So the ground state is a spin 0 state. This I will now construct the Lorentz generators, and we will see if we act on the ground state with the Lorentz generators, it will be spin 0. So when we act on the ground state with all creation operators are vectors in space-time. So these are vectors, so they do not change the integer character of the spin. So if I start with a spin 0, then I start with a vector, I get a spin 1, and with 2 vectors I get spin 2. So in the Navier sector, all states have integer spin. So in the Ramon sector, the ground state is so this index A is an SO d minus 1,1 spinor index. So this state transforms as a spinor, SO d minus 1,1, and so they are fermions. And I will show an explicit representation of these states to convince you that when we act on this state with the Lorentz matrices, we get spin hat. Okay? Okay. So as I said, the oscillators also in the Ramon sector and in the Navier sector, in both sectors, the oscillators are all space-time vectors. So if I start with a ground state, which is a spinor, all the excited states will be spinors in the Ramon sector, unlike in the Navier sector. So the ground state, the character of the ground state determines if the state is a boson or a fermion in space-time. Okay? So the Navier sector in the open string, the Navier sector will give me all bosons in space-time, and the Ramon sector will give me fermions. And in the closed string, if I take products of bosons and bosons, so Navier will give me bosons. If I take products of fermions times fermions, I get bosons. So Ramon sector gives me bosons in space-time, whereas Ramon Navier, which is fermions times bosons, give me fermions, and similarly Navier Ramon give me fermions. Okay, so Now, the important thing here is whether a state belongs to the Ramon or Nuñez sector. It depends on the ground state it is built in. Okay, so we define a ground state. The ground state is annihilated by all annihilation operators. We construct the Hilbert space in this way, but we still need to impose the constraints. Okay, so similarly as in the classical theory, we need on the solutions, on the classical solutions, we need to impose the constraints, the Virasoro constraints. Here, we will have to impose the super Virasoro constraints on the states of the theory. Okay.
Para ver si está entendiendo la idea. Uno parte con, por ejemplo, con bosones y fermiones, pero fermiones en el sentido de la worksheet. Uno parte de eso en la superstring y después cuando encuentra el espectro, por ejemplo en Nuñez, encuentra que las partículas, no sé si físicas o cómo llamarlas, pero las partículas en el espacio de tiempo, digamos, no son fermiones, sino que son bosones.
En el sector de Nuñez.
Claro, eso
cuando los fermiones en el worksheet tienen condiciones de contorno antiperiódicas, entonces se obtienen en espacio-tiempo estados que son bosónicos. En el sector de Ramón, que son modos enteros, uno obtiene en espacio-tiempo el sector fermiónico. Y en vez en el sector de Nuñez, donde los modos son semienteros, las condiciones de contorno de los fermiones en el worksheet determinan que el desarrollo en modos sea con modos enteros o semienteros. Y eso me determina en el espacio-tiempo que los estados que se construyen a partir del vacío van a depender del vacío. Pero el vacío en Ramón, en el sector de Ramón, es un spin-off. Si actuamos sobre este estado que voy a construir ahora con los generadores de Lorentz, me va a dar que tiene spin medio. Y como todos los operadores de creación son vectores, no le pueden cambiar la naturaleza. Entonces, okay. So, is it necessary that I speak English? Sí.
Acá todavía no tenemos supersimetría, ¿verdad? Eso lo vamos a deducir.
Claro, todavía no hay supersimetría. Todavía no construí el espectro. Estoy diciendo cómo construirlo.
Hasta ahora los vacíos que han definido son vacíos especiales. Son vacíos.
No. Estos son todos estados en espacio-tiempo. La masa, esta masa que definí acá, este operador de masa, bueno, de hecho este está acá, ¿no? O sea, el operador de la masa viene de este operador P cuadrado, es el espacio-tiempo. El P mu tiene el índice mu, espacio-tiempo, ¿no? O sea, este P cuadrado es P mu, y los índices mu toman valores de 0 a d-1. Entonces, esto define la masa en espacio-tiempo. Okay, so let me construct a particular representation of the Ramon ground state. This is the interesting part here. So we can define fermionic raising and lowering operators combining, so let me write here, combining the zero modes raising and lowering combinations of the zero mode operators. I here gets values from 1 to d minus 2. This is in general in d dimensions, okay? So I will consider the even. The even, we will then, later we will work out the critical dimension of the string, and we will see if it's d equals 10. But here, when we work with spinors, we have to make some distinctions with even and odd dimensions. Okay, so I will do this for even dimensions. Okay, so I define these fermionic raising and lowering operators constructed from the V naught. So, and in this basis, the Clifford algebra is like this. Okay, so, and this includes also the zero. So the Clifford algebra is just this anti-commutator. So we can define a highest weight state I can define a zero weight state, let's say a state which is annihilated by all the B minus operators. So B minus from this combination. So I start with a state which is annihilated by all B minus operators, and then I can construct a representation acting with the BI plus. Okay, so on this state, which is annihilated by all BI minus, I act with the BI plus. And then this gives a representation which has 2 to the B over 2 dimensions. Okay? Because I can. Okay, because I have d minus 2 over 2. Actually, I have d over 2 possibilities for this BI. I have d over 2. But then I can either act with it or not act with it. So it gives me 2 to the d over 2. Okay? So I construct this state, say for d equals 10, which is what we will be working on. I will define this state, which I will call S, which has 5 enters. This SI can take values plus or minus a half. So, and this BI plus convert a minus a half into a plus a half. So this state, which is annihilated by all B minus, would be the state with minus half, minus half, minus half. And then when I act with the BI plus, I convert the I entrance into a plus, okay? So this gives 2 to the d over 2-dimensional representation. Okay, so this is basically what is written here. Okay, so I start with this state, which is annihilated by all BI minus, and then I act with BI plus, and this raises SI from minus half to plus half, and so this gives me this representation where this SI can be half or minus half. So, for instance, this oscillator, if S4 is minus half, it won't be here, but if it is 1 half, then it will turn the fourth entrance here from minus half to okay, so this is, and actually this notation reflects the Lorentz properties of the spinor. So in order to see that this is actually a spinor, I can construct the Lorentz generators there is a representation of the Lorentz generator in terms of gamma matrices. So this is one representation of the Lorentz generator in terms of the d-dimensional Dirac matrices. So, okay, I won't write it, but these generators satisfy the Lorentz algebra, the SO d minus 1, 1 algebra here. And these generators, sigma 2i, 2i plus 1, they commute, so they can be simultaneously diagonalized. And then I can write an operator, so this, I can write this sigma 2i plus 1 in terms of the bi's, which I constructed here. So I can define this operator Si, which is a product of B plus, B minus, minus half. So one can see that this state is, so the ground state is a simultaneous eigenstate of the Si with eigenvalue Si. Okay. And then since Si is plus minus half, so you can see that this representation that we have written here is actually a spin and half representation. Okay, so these spinors form the 2 to the d over 2. If d equals 10, this is 2 to the 5th, so it's 32-dimensional representation of the Lorentz algebra. So d minus 1.
Sorry, 5 minutes.
Okay. Okay. Now the Dirac representation is reducible as a representation of the Lorentz algebra. And because these Lorentz generators are quadratic in the gamma matrices, then the spinors with even and odd numbers of plus a half do not mix. So we have one representation with even number of S of plus a half, and another representation with an odd number of plus a half, and these representations do not mix because the Lorentz generators are quadratic in the gamma matrices. So we can define this product of gamma matrices. This would be the equivalent of gamma 5 in 4 dimensions. So this is the chirality operator. It's a product of all gamma matrices in d dimensions. And I can write it in terms of this Si, which I have written before, which were the product. And this matrix has these properties. Gamma square is 1. Then it anti-commutes with any of the Dirac matrices, and it commutes with the Lorentz generator. Okay, so this gamma matrix has eigenvalues plus or minus 1. Okay, so and then it is diagonal, and it takes value plus 1 when the SA include an even number of minus a half and minus 1, so gamma acting on S plus 1 if there is an even number of minus a half Okay, so these 2 to the d over 2 states which have gamma eigenvalue plus 1, this, as I say, the gamma eigenvalue is the chirality of the state. So there are 2 to the d over 2 states with eigenvalue plus 1. They form a Weil representation of the Lorentz algebra, and those with eigenvalue minus half form a second inequivalent Weil representation. So this is familiar in 4 dimensions. In 4 dimensions, the Dirac representation is separates into two-dimensional Weil representations with different chiralities. So I have written the representation by the dimension. So the dimension 4 Dirac representation splits into a two-dimensional Weil representation with chirality plus 1 and a two-dimensional Weil representation with chirality minus 1. So I will put a prime when the chirality is minus 1. Okay? So similarly, in 10 dimensions, the 32-dimensional Dirac representation can be split into two Weil representations, each with dimension 16, one chiral and one with chirality plus 1, and the other one with chirality minus 1.
¿Qué sería 2 a la menos 1?
Yes. Okay. So, that much is for the Ramon ground state. Is it clear? Because it's usually complicated. But so the Ramon ground state is this 2 to the d over 2 representation of the Dirac algebra. And so now, if we want to construct the spectrum, and so we have constructed all these states. We define the ground state. We act on this ground state with the creation operators. But now we have to impose the superconformal constraints in order to eliminate the negative norm states. So recall in the bosonic string, we had these negative norm states because of the time-like component of the Minkowski metric. So this state, alpha naught minus m, acting on the ground state, has negative norm. So these states are ghosts, and so the theory is not unitary if we have these states. But in the bosonic string, you have seen that the Virasoro constraints are the physical state conditions, and they were enough to decouple all negative norm states. So what were, in the bosonic string, what were these physical state conditions? So so I guess you have seen for the bosonic string that if we implement, so the way to implement the Virasoro constraints in the classical theory were basically the vanishing of the energy momentum tensor, which basically means that all the modes of the energy momentum tensor, this is for all n, vanish. So the equivalent constraint in the quantum theory would be to ask that the Ln annihilate all physical states. So this would be the quantum version of the classical equation of motion for the metric. Okay. However, we will see in the bosonic string, I guess you have seen that it is not consistent to impose this condition for all n, because there is an anomaly in the Virasoro algebra. When you quantize the Virasoro algebra, you get this central charge term. Okay, so it is not possible to impose this condition for all n. It's inconsistent because then all states would have zero norm. So the most we can do is to impose this condition for positive, for the positive modes. So similarly as in the bosonic string, here our physical state condition will be that the Ln manipulate all physical states for n positive. Okay? And we also have for L naught that, well, now I call the normal ordering constant, I call it mu. In the bosonic string, you worked out this, the value for this mu, it turned out to be -1. Okay, remember, there are several ways to determine that constant. We will do that maybe tomorrow. I don't know how much time. Okay, let me just do this. And so, okay, so and for the closed string, we also have this condition. So these were the physical state conditions for the closed string. Now we have seen the classical superconformal algebra, but what is the equivalent of the central charge in the bosonic string? Here it will be a little bit different. We also have a central charge, but it is different from the bosonic string because we also have the contribution of the fermions. Okay, so I won't do the calculation. It's a long calculation. There are several ways to do it, but here you see that the central charge in the superconformal Virasoro algebra is d/8, and d/8, and then there is this m times m squared minus 2 phi, where phi is this phase, which is 0 for Ramon and 1/2 for Nuñez. Okay, so for Nuñez we get -1, and for Ramon this term is on there. Okay, so let me finish by writing the superconformal algebra, which will determine the spectrum of the theory. So we have also acquire an anomaly. So we have a different superconformal algebra in the Neves sector and in the Ramon sector. Okay, so this will determine that the physical state conditions will be different in the boson, in the Neves sector and in the Ramon sector. We will work it out tomorrow. But okay, but basically I wanted to do this. Okay, so there are several ways to obtain this algebra. One way is to take commutators between two states. So we use the commutators and anti-commutators, which we derived for the oscillators, bosonic and fermionic, and we sandwich it between two states, and then we obtain these central charges here. And an easier way to obtain this is to use superconformal techniques, but since we have not seen conformative theory in this course, I'm not sure, but it is really very easy to obtain this in conformative theory, basically by computing for those of you who know operator product expansions of the energy momentum tensor with itself, you determine the central charge, and from the supercurrent to the supercurrent, you determine this anomaly of the supercurrent.